Hi, I'm Nick van der Creek from Building Point Australia, and welcome to this Idea Statica presentation on sleeve connections. And as we can see in this illustration, a sleeve connection is quite simple in nature. We would typically have one or two structural steel hollow sections. In this case, I've got a couple of square hollow sections, and we would also have a joiner or a sleeving member. In this case, I've got an internal joiner of about 400 millimeters in length, and we could have bolts penetrating right through, as we do in this case, in perhaps horizontal and vertical planes, or in both directions if this is a column type of splice, or we might just have them in one direction like this. So to illustrate a couple of considerations as we work through such a connection, I'll build it up from scratch. And here I'm starting a new connection. And of course, in Idea Statica, we can pick our starting point. It could be an entirely blank workspace like this, or we could pick from a whole range of connections. And I'll pick from the beam to beam connections and secondary to primary beam, universal beam end onto another one. Here's a hollow section connection. I could use an end plate and delete that, or just start with a blank connection like this with square hollow sections. And I want to have a small gap between the members B1 and B2. And a fairly simple way, a nice way to create that is to start off with a working plane. I want to rotate that with respect to the global y-axis for 90 degrees like that. And then I can introduce some member cut operations like this. And we are going to cut initially B1 to the working plane and have a 5 millimeter offset like that. And then I'm going to repeat that cut operation and cut B2 a similar amount, but in the other direction. So that gives me a 10 millimeter gap between the ends of those two members. Now these members are currently 300 by 200 by 10. I don't want to use that size. I want to use a different size. So this section 10 in this file, I'm going to edit, and I'm going to pick from the Australian standard range of sections, and I'm going to select a 100 by 100 by 4. So here we have it, and I'm happy to use grade 350 on this occasion. And B1 is set to that size, and I'll make B2 set to that size as well. So we're getting a little bit closer. And when we add some other operations, we'll notice the length of these two members grows. It extends a certain distance beyond the last operation. And the next thing I want to do is introduce an internal sleeve. So these are 100 square sections by 4 thick. That leaves a theoretical 92 clearance here. I want to use an 89 by 89 square hollow section as the interior member. And we don't add another member in this case. We don't either add it there or copy an existing member and then make modifications. A member is intended to be loaded directly, and I do want to apply loads to B1, so it is a member, and the other member is supported. So in a sense, there'll be loads applied directly to that member via the support. Anything else, we want to use different types of operations. And when we want to use just a plate, for example, as part of the connection, we add a plate. We add a plate operation here. In the case of a different type of shape, but it's essentially like a plate, it's some component within the connection, we use a stiffening member like this. So we should think of this very much as a plate, but it can be of whatever shape we like, a universal beam, a hollow section like this, and so on. And in this case, I don't want it to be the same size, of course. I'm going to select plus, which gives me a new section altogether, and I'm going to pick from the library of rectangular hollow sections. And in this case, I'll select 8, so I get down to 89 by 89, and I'm happy to use the 6mm thick section initially and grade 350. So looking from this direction, I'm fairly happy with that setup. Maybe I'll edit that and try the 5mm thickness. That might well be enough. I can of course look at the results to see what the strength looks like and so on. And we select the home view. And the next thing is to start to introduce some bolt operations. So from the operation list again, we select a bolt grid or contact like that. And initially it's coming up with an error message, cannot execute the operation. I've got bolts, item count of two plates, and these fields are blank. So let's start to get that right. I want to go through 4 layers, and then it's defaulting to the plate icon here. Well, I want those to be parts of members in all cases. So I could now pick from the drop-down list for members. So if I hover over this face here, I see on the bottom left what it is, B1 Web 4. So I'll use that option here to start the bolt operation. And it's giving me that face there, and we see for B1 that Web 2 is also selected, in fact, for the next 3 fields. But what I'll do with the next operation, I like to keep them in order, is even though this next item is not a member, it's a stiffening member, we'll find it in the drop-down list for members. So if I hover over that, I see it's SM1 Web 4. But what I'll do this time, instead of picking it from that list, is use the pick tool like that, and it might make things easier. And similarly for the next one, pick that face, and just to confirm the last one there. So we can review these details and hover over, look at the bottom left, or just have a look at the selected items in orange and make sure that that bolt operation is correct. And the transparent view is quite handy. I want to select the stiffening member, either select it directly like that or select it here. And I want to make this 200mm in length each side like that. And getting back to the bolt operation, it says 50 from the cut end. I want to use an M20, that's what I've got, and I'll make that 35mm. And then the next spacing I'll use of 120mm, say, that type of thing. So what I'll have is 40mm from the center of the splice to the first bolt, enough edge distance for an M20 bolt, 120mm, and that leaves me another 40mm from the 200mm half length of this stiffener. So 40, 120 is 160, another 40. So I'm happy with that arrangement. And that second bolt will go through all of those layers just like the first one did. All of the bolts like this will be the same in that sense. And when I'm happy with that bolt grid arrangement, I can copy it, and then I get a duplicate. And the idea is that we change some details on the new item, or on one of these items at least. So what I want to do here is just make a few changes, and for grid 2 I'm going to pick this face of B2, and let's see what it's done. Going back to the solid view, so let's just go through it and make sure that we have all of the items correctly selected for this second bolt grid arrangement. So the first item looking on the bottom left is B2 Web 2, stiffener or stiffening member 1 Web 4, Web 2, and B2 Web 4. So happy with that. Okay, now I want to get some loads on this, and let's turn on the local coordinate system so we can just confirm the correct directions of load. And so the major axis moment is about MY in this system. And so for B1, I want to enter 10 kilonewton meters like that, and a negative V Z value of, well, -5 kilonewtons, like that. And we can have a look, as always, at the bending moment diagram. We select the wireframe view, the load, and then the member in question, and we can see the bending moment 10 kilonewton meters at the node, and we'll have shear constant all the way through this connection from the right to the left, and the bending moment applied to the right hand end of this little model is slightly less because of the presence of shear, such that we get the correct bending moment at the node as per our required setup. Now, I don't want to just stop there. We could perhaps try it like this, but I guess one of the things that we might tend to want in a sleeve type of connection is some contacts, some additional contacts. And when we have bolted items, we get automatic contacts. So as long as the distance between these surfaces is within 2 millimeters, we get an automatic contact there, and we'll get an automatic contact there. And in fact, if this gap is too big, what we tend to get is a singularity, and that would be a horizontal instability, effectively one member sliding along the bolt with respect or compared to other items in this connection. So you may well get an instability when you run the analysis for this type of connection. But I notice if those clearances are within the 2 millimeters typically, we tend to be okay. But what I want to do is add some further contacts at the top and the bottom, so that when we have the bending actions occurring, that these faces, these surfaces can come into play to help resist the bending moment. So this, I guess, is one of those options. You could consider that the presence of contacts or not. And the way to add additional contacts, bolts give you these automatic contacts. There's a couple of situations where you get that, but we can add further contacts by using either the bolt or the weld operation, but it's important to select the right one. So where we have two layers, two plates effectively, or a plate on a flange, two flat surfaces that are essentially in contact across their surface, then these items could be bolted, and in that case we select that operation and specify that it's going to be a contact instead of a bolt. And we can also select anchors with this type of contact as well. And then it's just like the bolting operations, we select the appropriate surfaces. So again, we want to make sure we're going to pick from members and use the pick tool. I'm going to select that flange there, and the next one is going to be the top flange of the stiffening member, like that. And we happily see the shaded red area where these items overlap, and this is what we get for these additional or specifically added contacts in Ideostatica. In the transparent view, when you select the operation, we see that contact area shaded in red. And just like before, we can copy an operation, change something, select that, and we get that area set up as a contact as well. So on this end, we'll have contacts left, right, top and bottom now. And so it's simply a matter of copying these operations to do it, to achieve a similar arrangement on the far side as well. So copy 3 and also copy 4. And so for this one here, I'm going to change the first item to be the top flange there, like that. And for grid 6, I'm going to select the first item as the bottom flange over here, and we see the surface there. So just quickly checking that we have those things, that we have those contacts set up correctly. Just select them all in turn. So I'm happy with that arrangement. And so at this point, we're ready to set the analysis running. So I'll press calculate. And we see here we've got green ticks, no red crosses. I haven't carried out a buckling analysis. I could do that, of course. And geometric and material nonlinear analysis has been used because we have a hollow section as a bearing member. And let's have a look at some results. This is the von Meyer stress, and I've got mesh and deformed geometry turned on. And we see some higher stress areas here, perhaps to do with internal contacts, and also here, and then naturally around the bolts and so on. We can have a look at the plastic strain. We see on the top left that we've got plastic strain up to 3.9% somewhere, and here's the plastic strain view. There's a bit happening again near contacts by the look of it, and also well, on the top flange, and also in contact areas in the bottom flange. We can also have a look at stress in contacts, and we see here a few contact points or stresses in certain areas. I can select that internal stiffening member and see that the maximum contact stress on that stiffening member is about 65 megapascals, and we can see that pattern. And of course, I could delete parts of the exterior cross section to have a further look at the interior member and some of the results. And we could have a look at bolt forces, of course. In fact, that's probably quite worthwhile doing. And I've got M20 grade 8.8 bolts here, and we can see that we've got shear in a number of different planes. So each bolt has 3 zones, if you like, of shear. The left zone, as we're looking at it with the mouse cursor, about 15 kilonewtons of shear on B1, and then in the interior of the stiffening member, we've got 0 shear, and then another 15.2 kilonewtons on the other shear surface. So for each bolt, we've got 3 shear results, and in terms of the overall check, the most severe result is considered. So there's a range of ways to have a look at this connection, and after just checking buckling, if we feel we need to, this situation is fairly compact, then we could be satisfied with the design and proceed to a report and so on. And we notice if we go to that report that we do get a comment. This bolting arrangement is not the normal setup that codes such as AS4100 have expressions for. And we do see this extra comment here in the report that there is a gap between connected plates and bolts should be designed as pins, provided resistances of bolts in shear and plates in bearing may be incorrect. So the clamping forces from bolts give the normal bearing capacity associated with the code expressions. Quite a high factor, 3.2 factor comes into it in the bearing checks around bolts, and there's no significant bending considered for bolts, or if it is in the code expressions, it's already factored into the bolt shear expression. So we might have a bit more bending in this situation than what is considered in the standard. And so, for example, we've got this open zone in the internal sleeve, and so a small eccentricity between the square hollow section sidewalls will lead to some bending, uniform bending perhaps through the interior of the bolt. So the software Ideostatica does not consider this bending effect, and so this is one of the aspects of looking at the bolts as pins. This bending may not be very severe, but a hand calculation or a check is required nevertheless. And as mentioned, the bearing capacities, because there isn't significant clamping of these surfaces, is not correct in the software checks because it's assuming a normal type of fully clamped bolting arrangement. It's up to the user to make some additional checks there. Okay, so that's the square hollow section, and we might want to use the same sort of connection for a circular hollow section. So let's set that up. So I'm going to try to start with this connection. I've made a copy of it, and I'm going to proceed to make some changes. So for this member B1, I'm going to change it, add a new cross section, and I'll pick from the list again, and I want to try 114 by 5.4 as the exterior dimension, and the internal sleeve I want to use a 101.6 by 5 CHS. So that will give me a reasonably good amount of clearance, not too big, not too small perhaps. So again, I'm happy with that grade like that, and I want to apply that same section to the other side as well. And for the interior sleeve, I want to change it to a slightly smaller section, and I want to use the 101.6 by 5 CHS like that, and of grade 350 again. So looking at it from the end view, we see the clearance looks about right, and I've got a number of errors, and it might be because I need to repeat those operations, or we might have something else going on here. So let's have a look at this first bolt grid. We're getting an error indicated for that. Sometimes because we've made a change, we might need to refresh this, and we do that by copying it. We'll get a new version of it, and that might give us a little bit more success. But we don't in this case. What we find is we can't specify specific arcs of circular sections like this for putting bolts through it. So we need to take a different approach. And what I'll do is go back to the previous connection where I've set this up like this, make another copy, and I'll have another go at this. And I'm going to use a polygon to simulate a circular hollow section. What we need is a decent amount of flat width there so the bolts can go through. And so it's not an exact CHS, but we can perhaps get something that's reasonable or reasonably close to the desired circular hollow sections. And what we notice if we simply select a polygon is that, perhaps I'll show this. So the outer radius, or the radius of the outer section of 114 divided by 2, essentially, and I want to use a relatively small number of sides, so I'll use 8, and a thickness of 5.4, and a small inner radius, so I don't get small arcs at the corner there, grade 350. And I notice that if I do it like that, I get the vertices at the sides, and that means I can't put bolts through horizontally like that. So here's perhaps another little trick that we could utilize. So again, for this member B1, I want to use the same section, but I want to rotate it slightly. And well, just to illustrate, I don't want to rotate it in this location here of 45 degrees divided by 2, 22.5, because that rotates my axis of loading like that. So I want to maintain that in the direction that it was. And so I'm going to use a different method to create this cross section, and I'm going to use the general cross section editor here, but still use a polygon like this, and its outer radius is 57 millimeters, 8 vertices or sides, thickness of 5.4 millimeters, and a small inner radius like that. And here we have it. And what I can do here is offset this, rotate it, and so on. And so here I want to enter the required rotation like that, and we see that we get the sides vertically and the top and bottom horizontally like that. So I'm happy with that. And so there's our section 16 general, and I'll make the other side the same like that. And now for the interior stiffening member, the same sort of idea. Add a new section, welded general cross section, cold formed polygon, and this will be essentially 102 diameter, 51 radius, thickness of 5, small internal radius here like that, and again a 22.5 degrees rotation like that. Right, so we're getting closer. That doesn't look too bad from that direction. Obviously my bolts are now defaulting to the other faces that were there already, and I don't want that. And what I could see if I could do is change these grid details, and I'll pick grid 1 and select that surface, B1 Web 7. Next one is SM1 Web 7, SM1 Web 3, and B1 Web 3. So that's fine. And let's look at the next grid. And I want to pick that item there. Spin that around. And they're all orange, so that looks good, but I'll just have a confirmation. B2 Web 3, stiffening member 1, Web 7, Web 3, and B2 Web 7. So happily, that's fine. Sometimes we might need to right-click, copy this operation, untick or delete the earlier one, so that operation is refreshed, and it allows us to specify the correct faces, because we might have more faces on the new cross-section shape than were available to that grid operation when it was originally created. That's the reason, and the lists aren't entirely refreshed all the time in this situation. So now we could have a look at the contact operations. So let's go back to the transparent view. We'll get automatic contacts where we have bolting, and that grid operation is going to be automatic anyway. That wouldn't be a problem. We wouldn't get an error with a double up like that, but we really want it to be on a different face. So let's see if we can make the change here. Select that outer surface, and the inner one is going to be that stiffening member like that, and that works. So it was just a matter of going through this, and to save a little bit of time, I'll go back to the same arrangement in a different connection in this file. I increase the loading slightly because we have a slightly larger section. So instead of 10, I've got 15 kilonewton meters and a slightly higher shear. And so again, it's just a matter of running the analysis. This time I'll run the buckling analysis as well. So you do that from the check menu and the drop down, and we'll see how this one goes. Now, I've only got contacts, well, the automatic ones where the bolts are, and top and bottom flanges. We could also set up surface contacts on the other sides as well. So that's another 4 on each side here and another 4 there. So another 8 contact operations will complete this connection in terms of all of the contacts. And so the same as before, after the analysis, we can review the behavior, review the results. That's equivalent stress, plastic strain. There's a little bit going on by the look of it in the internal joiner there. Plastic strain of up to 4%, so getting close to the limit of 5%. And let's have a look at contact stresses like that. We can see them on the exterior. We can see some in the interior, As mentioned, I haven't put contacts on all surfaces, so we see some strips where there's no contact stress. Those volumes could essentially overlap a little bit right now, but as I say, we could add some contacts if we need to. Everything's working, so it's not as if we need any more strength right now. And finally, we could have a look at the buckling modes and buckling load factors. So here we've got a high buckling load factor, the minimum. Above 3 for a situation like this is fine. So we're easily high enough with our buckling load factors. And just like before, I could delete some of the exterior member to help us visualize the buckling mode of the interior stiffener, but very compact, very solid. This is nothing to be concerned about at all at a buckling load factor of 20. So that completes the presentation. Thank you for your interest. And of course, if you have any questions about Idea Statica, please give us a call at Building Point. Thank you very much. Cheers.